All right, we're picking up from the last lecture in which we were looking at buffers. And this is a little bit of a complicated topic. So it's one of those things you're probably going to have to run through it a few times or stop the video and kind of go over things to have it make a little more sense. What we were discussing is a titration. And I don't know how much experience you had from titrations from last year, but the idea is that you are reacting to things. A simple titration, which we're going to look at in this very particular example, is, for example, we have a weak acid and we are titrating it with a strong base. Now remember that strong bases and strong acids, they both go 100% to completion. So there isn't that equilibrium back and forth thing. It goes all the way to completion. In this little example, you'll be left with the conjugate base and water. Yeah, it goes all the way to completion. Now, a buffer is something, as we mentioned in the previous lecture, where you have the combination of a weak acid and its conjugate base. So here is our weak acid, and here is the conjugate base of the weak acid. So these two guys, neither one is fantastic at doing much of anything. They just kind of hang around. The weak acid will donate a hydrogen, but it doesn't do it well. And this is kind of just the opposite. Now remember, something we mentioned before is when you have these two guys together, their product will equal KB. KB. So Ka times Kb is equal to Kw, 1 times 10 to the negative 14. That's how these two guys will relate to each other. If I know one, I know the value of the other. If I'm looking at this equation here, something that's very interesting is if I have equal portions of the base and the acid, of course that's 1, and then the log of 1 is 0. So at what I would call a perfect buffer, in other words, it's equally positioned to resist changes in pH because of the base and equally resistant to changes in pH because of the acid, 50-50, if you will, equal parts of these two guys. At that point, the pH is equal to the pKa. That is a classic AP question where they don't give you the pKa, but they give you a bunch of other information. And what they're telling you is to utilize this equation. And if I can figure out what the pH is, and I know I have equal portions of acid and conjugate base, I know what the pKa is. Therefore, I can do the whole anti-log thing to figure out what the Ka value is. Okay. Now, here's another tricky question for you. Using this titration curve, where on this curve, or what pH, let's call this 7. I'm gonna call it 8, just for fun. Where on this pH scale, ballpark, would be the location of a perfect buffer? Now, many of you may be saying, well, clearly at the equivalence point, because what's going on at the equivalence point? We have equal parts, moles, of the acid and OH. So be very careful what base you're talking about. What happens when you have equal parts acid and base? Give it a pause. Your answer should be this is 100% gone, and all of it has been transferred over to the conjugate base. So it's gone. So that is not the answer. So if we're talking about a perfect buffer, where should that be? Let's just pretend that this is 20 mils. Well, if it took me 20 mils to get rid of all of it, and a perfect buffer is 50-50, then I really want to be at about 10 mils. Because at 10 mils, I have removed half of the acid and have transferred it over to the base because of the completion aspect of OH. It'll take whatever you give it. So if I take half of it's over here. So now I have a 50-50 split. And of course, that'll be 1, and the pKa is equal to pH. So at that point, if I were to carry this over, and let's just pretend this is all the same, my pH would be about 4, in which I have a perfect buffer. So if I know what the pH is at the buffering point, it's right here. Okay, let's move along and we'll knock out some more of these questions as we go. We'll do one more example, then we'll bounce back over to the homework problems. For the next one here, we're going to talk about preparing a buffer. The question is, how many moles of NH4Cl must be added to 2 liters of 0.1 molarity ammonia to form a buffer whose pH is 9.00. Tricky question. On your own, this probably would be kind of difficult. We're going to step through it and see how we could kind of approach this one. This 2 liter thing will come in towards the end. We're not going to hit that initially. This piece of information is handy. This piece of information is very handy. Let's go ahead and just kind of make a rice table. I always say, when in doubt, make a rice table. It may not be all that helpful, but maybe it will. We'll write in the weak base, and if we're talking about a base here, bases always have to have water because it needs to take that hydrogen from somewhere, and that's going to be water. So having these 2 guys together, it does its base kind of thing and takes a hydrogen off of water, and there's its equation. Okay, now starting off, we can see if we can throw anything in here. I have some ammonia. Fine, I can ignore water. The ammonium, if we go, how many moles of this stuff do we need? I don't know. I don't know how much that is. That's none of it. So I know I'm going to have this buffer of 2 of these guys, the weak base and its conjugate acid. But I don't know how much I need. That's the whole question. And I need it in moles. But that's what this is going to come in. We'll get there. I don't know what this value is. We're actually starting off with, I didn't add any, so I don't have any to begin with. All right, this is going to be the part that's a little weird. It's very algebra-y. I need 2 variables because this is what I'm starting with. I need to know what this is, but the base is going to do its thing. It's going to dissociate. So I'm just going to add in this extra separate variable. But we're going to treat it just like we've treated the other ones. It's just insignificant. And again, it's doing this thing, whatever. So its amount that we're subtracting off here, it's real. We're going to find out exactly what it is, but it's insignificant compared to this value. So if I subtract it, it doesn't change much. And that's going to be very helpful for here because I can just ignore it and not have 2 variables floating around. It's just x. And then over here, oh boy, what's this number? We have the pH. So if I have the pH, which is 9, that means 1 times 10 to the negative 9 is the hydrogen ion concentration. So therefore, this value must be 1 times 10 to the negative 5. And again, the reason I get that is 1 times 10 to the negative 14 is for water. And if I know 1 hydrogen ion, I can turn that into the hydrogen ion concentration doing the anti-log thing. And then I can divide this value by 1 times 10 to the negative 9 to get this value. All right, I got something to work with here. The last thing is I'm going to rearrange this equation and solve for, well, I'll just kind of show it here really quick. Kb is equal to NH4 plus OH minus over NH3. So that's our equation, but really what we're trying to figure out here is how much NH4 do I need? That's the question up here. So if I rearrange this around a little bit and solve for the NH4 plus, all right, I had to pause it there for a second. So if we rearrange the equation and solve for the NH4 plus, we're going to have to bring a couple things over to the other side, and we'll do that right now. So we will have NH4 plus is equal to 1.8 times 10 to the negative 5. And that's the value we just grab out of the back of the book. It is the Kb value for ammonia. And we use the concentration of the NH3 that is given to us. And we put this over the OH value. And if we solve this, you end up with 0.18 molarity. And this is the value for the NH4 plus. And again, this is for each liter, each 1 liter, because it's a molarity, moles per liter. We want to know what it is for 2 liters. And that's going to give us 0.36 moles of NH4Cl, actually. So that's actually how much we need to find that value. Okay, so that one is done, and we're probably at the end of this lecture, so we will make a new one.